I'm Jack Dongarra. I work at the University of Tennessee and Oak Ridge National Laboratory. I also have a position at the University of Manchester. I'm in the Electrical Engineering and Computer Science Department at the University of Tennessee, and my area of interest is really in developing a high-quality mathematical software for high-performance systems. And today we're looking at the use of multi-core and hybrid systems. We feel that that technology is really going to be the technology that's used in high-performance computing in the future. We're starting to see more and more of these systems, hybrid systems, coming into play with respect to high-performance scientific computing. If you take a look at the top 500, 2 of the machines in the top 10 are based on hybrid systems, and we're going to see more of that clearly as things unfold and unroll, as new products are formed, and as standards for hybrid technology really get put into play. We are interested in the development of numerical libraries, in particular looking at linear algebra problems and how they would fit into today's architecture. So we're trying to understand what we need to do to redesign those algorithms so that they work on multi-core and accelerator-based technologies. What fundamental structures are needed to be changed so that we can extract the performance that those architectures provide, and do it at a level where users can easily get access to it. So we are currently rewriting and restructuring some of our packages. We've been involved in the development of packages like LAPACK and SCalaPACK, and those packages are undergoing radical changes based on the use of multi-core and the use of hybrid technologies. Today we're looking at multi-core systems where using GPUs as the accelerator and trying to understand what we need to do to effectively use both the multi-core and the GPU components of that system. As the hybrid architectures play more of a role in terms of scientific computing, we see them at all levels of the computational scale. That is, we see them on small systems where we have a few multi-core chips tied together with GPU accelerators, on medium-sized systems, and really at the extreme. So our software is intended to run across that scale. That is, working on systems which have a few chips, a few sockets of multi-core with GPU accelerators, up to the point where we have exascale systems. And those systems will, by necessity, be based on the hybrid model, using multi-core chips and using these accelerators to effectively gain performance. And our software has to make that transition. It's a challenging thing to get software to run at that level, and that challenge, a number of us are taking on that challenge to ensure that there'll be an adequate numerical library for some of the most challenging computational problems that people will put onto these machines. The projections for future systems show an incredible situation. We're looking at exascale computing. So exascales 10 to the 18 floating point operations per second. And we see that coming into play roughly in the year 2018 to 2020. Exascale computing will have us at a situation where the level of parallelism that we will encounter in terms of our applications running on those systems is on the order of 1 billion threads of execution. And understanding what programming models we have, how the applications can be written, what needs to be done to address issues such as fault tolerance are going to be critical when we get to that scale. Thinking about billion-way parallelism, using hybrid technologies to accelerate the kind of things that we're thinking of doing on these systems is going to be just critical, and understanding how they all fit together is really one of our challenges for the future.